Welcome to Hardening OpenZFS to further mitigate ransomware for the SNIA Storage Developer Conference 2021. My name is Michael Dexter and I provide OpenZFS storage support professionally, and I'm a member of the SNIA Data Protection and Privacy Committee. This talk is designed to complement another DPPC talk at the same conference, Ransomware, an analysis of practical steps for mitigation and recovery, and will focus on the open source and vendor-neutral OpenZFS file system and volume manager. For context, the SNIA definition of ransomware reads, software that uses encryption to disable a target's access to its data until a ransom is paid. There is no guarantee that payment will result in the necessary decryption key or that the encryption key provided will function properly. In short, the malicious separation of you from your data, often with unfulfilled promises of returning access to you or not publishing it. For those not familiar with OpenZFS, I will provide a brief introduction. The OpenZFS file system began as a proprietary file system for the Solaris operating system and was open-sourced as part of OpenSolaris. It has been ported to at least 5 additional operating systems, making it the most portable open-source enterprise file system available. OpenZFS is open source per every major definition and is vendor-neutral, enjoying support from projects and products around the world. Technologically, OpenZFS offers continuous data validation upon both write and read. It is highly scalable without performance penalties, is highly flexible for hybrid spinning disk and flash media, and provides efficient snapshotting thanks to its copy-on-write architecture. It is important to point out that ZFS was not possible prior to around the year 2000. CPU power could not be wasted either calculating and validating checksums or performing compression and encryption operations. Today's CPUs actually increase storage performance thanks to continuous data compression, because the CPU will always outperform the storage hardware. File system portability was also rarely a priority, with file systems having a one-to-one relationship to operating systems. Flash acceleration was also an exotic, non-standard option and was completely impractical for primary storage. And of course, open source was the rare exception in enterprise storage rather than the norm. Looking at what is now possible with OpenZFS, OpenZFS provides affordable snapshots with no performance penalties, with snapshots providing the perfect foundation for data replication. OpenZFS is completely hardware agnostic, and hardware RAID cards are strongly discouraged for use with OpenZFS. Hardware RAID had a good run, but the rest of the computer caught up with it in terms of performance and redundancy. OpenZFS is highly portable between operating systems, with only enabled features determining importability of a given storage pool. And above all, for the purpose of this talk, OpenZFS provides a robust administrative layer below the user-facing POSIX layer. Operating below the POSIX layer. You know the POSIX layer as files and folders, plus their permissions, access control lists, extended attributes, and more, and traditional file systems are designed around them. OpenZFS, on the other hand, is fundamentally an object store with POSIX support as simply a compatibility layer. This design allows for synthetic block devices in the form of ZVols, or ZFS volumes, and the Lustre distributed file system is now able to speak directly to the OpenZFS Data Management Unit, or DMU layer. By operating below the user-facing POSIX layer, OpenZFS enables dynamic administrative operations that were once highly disruptive. The immutability of data, or read-only state, and visibility of data, by being mounted, can be easily set in real time without the traditional full unmounting and remounting of file systems. In addition, parameters such as executability, compression, block size, synchronous behavior, access time, can all be modified at any time without disruptions. With that in mind, let's look at how users around the world are mitigating ransomware using OpenZFS snapshots and replication. This is based on real-world scenarios I see every day. Unlike many file system snapshotting technologies, OpenZFS provides efficient point-in-time snapshots without performance penalties. Any given snapshot is a delta of the changes to the previous snapshot and is subject to all of the integrity guarantees provided by OpenZFS checksum calculation and validation. OpenZFS snapshots are immutable by design, but can be made writable with clones, which can provide the foundation for, say, virtual machines that are based on a common golden image. As efficient deltas of data changes, snapshots provide the foundation for OpenZFS replication, with which they are sent to another OpenZFS system for a verifiably block-for-block identical duplicate. To benefit from OpenZFS snapshots in practice, you must first select a network-attached storage or general-purpose operating system that supports OpenZFS. You must select quality hardware. I cannot emphasize this enough because OpenZFS works hand in hand with hardware to provide reliability guarantees. You must choose SAS, SATA, or NVMe devices that will deliver your storage goals, and from there you achieve your redundancy goals. OpenZFS supports redundancy through mirroring and distributed parity, and there are a number of best practices to consider. I strongly suggest N+2 redundancy, meaning that 2 drives can fail within a given redundancy group, or virtual device, or VDEV for short. Redundancy is achieved in VDEVs, and scalability is achieved by striping VDEVs together. Avoid using more than 9 devices per VDEV, and stay consistent with that count. Triple mirrored VDEVs will provide excellent performance, but most bean counters will scoff at the balance of capacity and redundancy that provides. The resulting array or Z pool should be snapshotted at least daily, but the frequency can be hourly or even a matter of minutes, depending on your restore point objectives. The resulting snapshots should be replicated to a second and preferably a third system to achieve meaningful backups. From there, data can be replicated to a cloud provider using object storage solutions. This storage infrastructure can be then shared out with your sharing protocol of choice, be it SMB, NFS, FTP, or just about any protocol that can operate at the POSIX level. Alternatively, block storage can be provided over iSCSI or Fiber Channel, and object storage both at the DMU layer and anything else that can talk at the POSIX layer. If you can share it from POSIX, you can back it with OpenZFS. This raises the question of how long to retain your OpenZFS snapshots. The number you keep is only limited by your hardware. A large number of snapshots may be slow to list, but do not fundamentally impact performance. Some organizations are subject to external retention obligations, and I have seen these be up to a year or more, including a school district that wants to keep everything for 100 years. Now that's not practical on any system I will describe, but it's something to keep in mind. Either way, the perfect encryption-based ransomware storm comes from a bored user on the Friday before a long holiday. They're watching cat videos or rummaging through their spam and unknowingly initiate a ransomware attack. Everyone goes home and the attack proceeds to encrypt everything they have access to and goes unnoticed until everyone returns to the office after the holiday. Consider a snapshot retention policy that is a minimum of your longest holiday plus a week. This all represents a very good start. Variations on this strategy are used around the world, and when hit by ransomware, the infected file systems, or datasets, are simply rolled back to a point before the attack occurred. Data that was infected after the most recent snapshot may be difficult to retrieve, as with any data that is in flight. Some users preserve the infected state of their data for forensic analysis, continuing their production use with writable clones. At this point, everything is a matter of time, how frequently you have snapshotted your storage, and how quickly you can return to a working state. In short, Data Protection 101. Now on to OpenZFS ransomware mitigation tomorrow and beyond. Easily recovering from ransomware attacks is a good start, but I'm sure we can do better. Let's take a moment to think about who is the greatest threat to your data. The online format mercifully spares you from having to raise your hand when I ask, but have you ever accidentally deleted data? I sure have, and note that zero malice nor a third party was involved. Has your email client ever auto-completed the wrong email address? If so, you may have exfiltrated sensitive data, again, without malice and without a third party. Have you ever had a storage device fail with no chance of recovery? That too doesn't require an attacker. And worst of all, have you ever locked yourself out of your own encrypted storage? Congratulations, you just provided the perfect encryption-based ransomware attack with no one standing by for a ransomware payment. It's just as much a matter of us versus us as us versus them, and the professionals are simply more efficient at performing all of the damage I just described. For this reason, I consider the majority of ransomware protection to be good traditional data protection practices. That said, never forget the fundamentals of securing your data. You don't need a computer to exercise the principles of need-to-know information and access based on least privilege. Some will argue that as long as you are alerted to the safecracker before they finish their job, your safe is secure by definition. In computer terms, it is good to block all on your firewall and open up access as needed, with the same being true of storage. Stay up to date with the software you use, and of course teach your team to be skeptical about everything from email attachments to phone calls from people claiming to be from the company support team. You're probably pretty good about these by now, but take time to learn your data. Inventory it. Validate it. You know it best, and only you can determine if it has been tampered with or not. That all said, let's update our expectations now that we are armed with the OpenZFS hammer and we can search for nails to hit with it. The ransomware mitigation strategy I described has proven quite good, but is only a matter of time before limitations are found and OpenZFS itself is targeted. I propose that we first reduce ransomware attacks to the level of tolerable petty theft and vandalism, rather than the disastrous force that it is today. Ransomware should not cause organization-wide disruption. If it does, you are probably not prepared for storage infrastructure failures that require zero malice. Looking ahead, equipped with OpenZFS, I propose that we first look at leveraging the OpenZFS management layer to the greatest extent possible. Remember that data immutability, visibility, and executability was anything but dynamic to change. You had to unmount and remount file systems to change these, and that was highly disruptive. Embracing this fact, remember that read-only data cannot be encrypted and invisible data cannot be exfiltrated. With OpenZFS, one simply sets a dynamic parameter to change read-only immutability, or unmounts a dataset to make it invisible. If your use case and application allows for it, automatically tier data immutability and visibility by age. Consider an immutability window for data as it ages and simply lock it up automatically. This may inconvenience some users who stray from their normal behavior, but the occasional inconvenience is better than organization-wide disruption. From there, proactively set immutability in response to anomalous activities. A ransomware attacker wants to be fast and far-reaching. The more comprehensive the attack is, the higher the potential ransom payment. Remember the petty theft and vandalism analogy and the goal of reducing ransomware attacks to being equivalent to it? All but the slowest of encryption-based ransomware attacks have recognizable traits. The encryption requires CPU resources which are measurable and may be noticeable to users. The resulting overwriting of good data with encrypted data appears as increased storage load. Users may even notice unusable data prior to the infamous "your files have been encrypted" screen. So watch for those patterns and react to them with an alert and the instant immutability of the affected storage, which is now affordable thanks to OpenZFS. Empower your users to set off an alarm if they see something suspicious, just as they would with an intruder in the real world. This is all known as vulvation in nature. Various creatures curl up into a ball when threatened, and I wouldn't rule out your storage doing the same. You'll be glad you did, and it's only as long as needed. From there, learn to trust less. The era of granting team members unrestricted access within the castle walls under the assumption that the walls themselves and the moat will keep everyone at bay is no longer adequate. NIST SP 800-207 is vague about how the concept of zero trust applies to storage, but it's a step in the right direction. In layperson's terms, consider the difference between giving your teenager money when they ask versus giving them a payment card without limits. Enact such controls with your storage, such that multi-factor authentication is required to gain access to certain, if not all, storage. Start with minimal access and grant more as needed, revoking it when the task is finished. And finally, human error alone and sabotage are reasons to habitually trust less, beginning with yourself. I personally am not a fan of biometric authentication, as I prefer to keep the real world and the electronic world as separate as possible. You can consider eliminating all direct storage access through the use of virtual desktops. In the long term, the POSIX 1003.1e draft on ACLs could also consider access-based file and directory enumeration, or visibility, as is supported by the SMB protocol. The draft isn't finalized, so hey, why not make a few revisions? Either way, repeat after me. Immutable data cannot be encrypted, and invisible data cannot be exfiltrated. From there, let's look at securing the OpenZFS management layer, given that it's only a matter of time that OpenZFS itself is targeted. Here and now, OpenZFS offers administrative delegation to individual users who could be multi-factor authentication enabled. For me, this solves the age-old problem of how to back up a remote server over the WAN in a way that preserves administrative file permissions, but is retrieved by an unprivileged user. Narrow this kind of unprivileged administrative duties whenever possible, and ultimately I would like to see the ability to clip the wings of the omnipotent administrative user. You can also remove administrative binaries, but an attacker may bring their own. For this reason, operating system diversity is a proven exposure reduction strategy. OpenZFS excels in this regard, beat only by FAT32. I look forward to the day that OpenZFS operates everywhere and operating system diversity is a convenient line of defense. In the big picture, OpenZFS is only now truly gaining momentum. The different supported operating systems are gradually reuniting on a common upstream codebase, and I was the first user to use OpenZFS on Windows on real hardware. Looking ahead, OpenZFS contains most, if not all, of the counters needed to implement self-defensive vulvation, with which a file system kicks into read-only mode for a predetermined amount of time with a security notification. I would not rule out the option of requiring multi-factor authentication for all destructive storage operations system-wide, with the long-term goal of truly immutable storage systems. While geeking out, let's briefly discuss the threat of a poisoned replication stream. OpenZFS operates in kernel space for performance reasons, and one could theoretically send a malicious replication payload that could do significant damage. Here and now, OpenZFS features a pool-wide checkpoint that is essentially a snapshot of the entire storage pool that can be rolled back in its entirety. This feature, in conjunction with a virtual machine doing the actual receive, could add a layer of protection from malicious send streams. I, for one, think that OpenZFS and virtual machines were made for one another. Hypothetical slow-moving sleeper ransomware is also something to take into consideration. The definition may vary, but it implies that some form of time bomb goes unnoticed for future execution. My first response is to exercise good immutability and no-exec hygiene, and to realize that your very own older software installers may be your greatest liability. Keep in mind that the encryption of an encryption-based ransomware attack will always take place in the present, and it is always something to watch for. If snapshots are found to indeed contain malware or tainted data, there are various ways of redacting them through reconstruction. The OpenZFS redacted send exists for this goal and was designed to remove personally identifiable information from backups. And again, you know your data best, and only you can tell if your backups have been tampered with. The online nature of OpenZFS facilitates validation. The ZFS diff operation can help to some degree, and there's nothing exotic about checksumming and validating files at the POSIX level. Do air-gap your backups whenever feasible, but embrace the fact that unlike tape, OpenZFS provides online accessible backups. This means that a completely separate team could periodically or routinely perform validation operations like importing and querying databases, booting virtual machines, and performing external checksum validation operations. Such operations can take advantage of OpenZFS writable clones, be pushed to tape, or whatever else will help us achieve the ambitious goal of 100-year archival abilities. Hopefully this talk has broadened your thinking about how OpenZFS can mitigate evolving ransomware threats, and if I have helped you mitigate one attack, I have been successful. Thank you for attending, and you're welcome to reach out to me by email or on Twitter at @MichaelDexter.